Thank you, Professor Ito. I'm Junko Ishi-Hayase. It's my great pleasure to give a talk on my recent research here. Our research has been done in collaboration with Professor Ito's group and our group at Keio University and AIST and Hewlett-Packard Laboratory and ETH at Zurich. Today, I'd like to talk about the nanometer scale sensing of ultra-weak magnetic field using a single electric spins. Magnetic field sensing, such as NMR, has been widely used in the field of material science and medical science because it enables us to determine the molecular structure. However, there are some limitations. For example, low sensitivity and low spatial resolution. Our purpose is to go beyond the limit using quantum methodology to achieve the single molecular detection. In this study, we demonstrate magnetometry using single electron spin of the very weak magnetic field. One of the very promising candidates to achieve the quantum magnetometry is single electron spins of nitrogen vacancy center in diamond. We call this nitrogen vacancy center NV centers. By using NV center, we can measure the weak external magnetic field by measuring the change of Raman frequency of NV electron spin. This NV center has a lot of advantages. For example, NV center electron spin shows a very long coherence time, even at room temperature. This is very important to achieve the very high sensitivity of magnetometry. The another advantage is that the NV center in diamond can be placed near the measuring target if we can dope the NV center near the surface of diamond substrate. As a result, the diamond magnetic sensor should expect to show a higher performance compared to the other magnetic sensors. Our purpose is to achieve higher performance of diamond sensor to realize a single proton spin detection. Our technique to achieve higher performance is nitrogen-doped isotopically enriched CVD. Then we can achieve a higher performance by developing isotope engineering and doping engineering in nitrogen-doped isotopically enriched CVD method. Today, I'd like to show you the result of our doping control technique by using nitrogen-doped isotopically enriched CVD. After that, we show the first demonstration of magnetometry using our NV center sample. So first of all, I'd like to make a brief introduction of NV centers. NV center is composed of nitrogen and vacancy doped in diamond. The single triplet spin state of NV center can emit the single photons. This spin triplet state is a very stable single photon source at room temperature. And there is another advantage of NV centers. One advantage is that we can initialize and read out of single electron spins of NV centers by optical measurement at room temperature. And we can manipulate this spin triplet state by irradiating magnetic microwave field, and this spin triplet state shows a very long coherence time, which is of the order of millisecond, even at room temperature. This is a very advantage, which is realized only in the NV center in diamond. Because of the advantages of NV center of diamond, there is a lot of application using NV centers. For example, quantum information processing and quantum spin photon network and quantum magnetometry, which means nanoscale sensing of ultra-weak magnetic field. Today, I like to focus on quantum magnetometry. This ultimate challenge of this magnetometry is to detect a single proton at room temperature. Here we show some experimental setup to perform the magnetometry using NV center. For example, single NV magnetometry and NV ensemble magnetometry, and magnetometry using scanning NV center probe. So the important thing to achieve the higher performance is the long coherence time and near surface doping. These two factors is very important to achieve the higher performance. Moreover, density control and lateral arrangement is also important to some other applications too. So here we show the requirement again. To realize this requirement, we developed the nitrogen-doped CVD method. This technique is much different from the doping technique. For example, ion implantation, which is widely used to dope NV center in diamond. So first of all, I'd like to show you the ion implantation doping technique. This technique is widely used, and this technique is useful to dope at a specific position. But the problem is that the ion implantation in the ion implantation, the coherence time in the sample becomes short. The CVD method is another technique to dope the NV center in diamond. Especially isotopically enriched CVD is an effective method to obtain the NV center with longer coherence time. Other group reported millisecond order coherence time in isotopically enriched CVD diamond. However, in this technique, the doping control is difficult. So we developed this isotopically enriched CVD by doping nitrogen during CVD process. By doping nitrogen gas, we can control the doping position and doping density by changing the nitrogen gas concentration and growth thickness and surface termination and local of angle change. So first, we will show you the result of 5 nanometer nitrogen doped layer on the flat substrate. This figure shows a confocal photoluminescence mapping of this sample. And we observe many bright spots which correspond to the single photon emission from the NV center in diamond. So as a result, we can dope effectively in the thin layer on the diamond substrate. After that, we tried to fabricate more thinner diamond layer, which is 5 nanometer thickness layer. So also we can obtain many NV center in 5 nanometer surface layers. So the concentration of NV center is much larger than those in isotopically purified CVD diamond. So this figure shows a photon measurement in 5 nanometer sample. So in this sample, we cannot observe this oscillatory behavior, which caused by the hyperfine interaction with carbon-13. So this is a confirmation that the nitrogen legacy center exists in 5 nanometer surface layer. So this is a very surprising result because people believe the NV center cannot exist near hydrogen-terminated surface layers because NV center energy level is above Fermi level. In the surface layer, in the hydrogen-terminated surface layers. However, we can observe the NV center in 5 nanometer surface layers. The reason is that the high concentration, high nitrogen concentration in our sample push down the energy level of NV center below the Fermi level. So NV center can exist in 5 nanometer surface layer, even for hydrogen termination samples. So for further engineering of surface band structure, we tried to change the termination of surface to the oxygen termination. For oxygen termination, this band structure changed into like here, as shown here. So we expect the NV center exists in the region more close to surface. So this is the result. We can observe slightly increase of NV center concentration in oxygen-terminated sample. So this result demonstrates that surface band engineering by changing the nitrogen concentration and by changing surface termination is important for NV center formation near surface. So let's move on to the talk about the doping position control, doping density control. So here we show how to control NV center doping density. The NV center density is expected to be changed by changing the surface condition, because the incorporation of defect is strongly dependent on the surface condition, for example, of angle of substrate. So we try to change the off-angle substrate by using microstructures substrate. So we fabricate the diamond thin layer, nitrogen doped diamond thin layer on micro-patterned substrate. So this is a result. As you can see, the nitrogen NV center can be doped in a specific area, which is correspond to the etched area. So we can demonstrate the selective, spatial selective doping of NV centers by using the nitrogen doped CVD method on micro-patterned substrate. This is the first demonstration of lateral arrangement of NV centers fabricated using CVD. And this shows a spectral, photoluminescence spectra of this sample. The spectral photoluminescence intensity much larger in etched area compared to the photoluminescence intensity in non-etched area. This means that the NV center density is significantly enhanced in the etched area. This means that we can control the doping density of NV center by controlling the local off-angle arrangement of substrate by using etching technique. So we can control the doping position and doping density by controlling the surface condition or interface condition in nitrogen doped isotopically enriched CVD. Then let me move on to the talk about magnetometry. So first, I will show you the result of measurement of spin property of our sample. This figure shows the result of spin echo measurement in 100 nanometer sample. We can observe the very long coherence time of spin triplet state, which is of the order of millisecond. This is a comparable value to with the longest coherence time measured in isotopically enriched bulk diamond. So this result shows isotopically engineering is very important to obtain the long coherence time on NV centers. So we also measure the coherence time in 5 nanometer sample. Unfortunately, the coherence time is much shorter than that in 100 nanometers. This value is comparable to the value measured in ion implantation sample. So this value is not optimized, but anyway, we estimate the performance of 5 nanometer sample. The present status is here. So this is not sufficient to detect a single nuclear spins. So in order to obtain the further higher performance, we use a spin locking technique. This technique enable us to enhance effective T2, which is called T1 low. So now we try to demonstrate spin locking magnetometry in collaboration with Degan group at ETH. So this spin locking magnetometry, they called this technique rotating frame magnetometry, is just published in PRL recently. So now we explain briefly the rotating frame magnetometry. Here is a schematic of experimental setup of magnetometry. So if this electron spins, it's influenced by the small external AC magnetic field, the spin state will be changed. So we detect this change of spin state by optical measurement, and we manipulate this spin state by irradiating microwave field. So this is a pulse sequence used in the spin locking magnetometry. So here is the principle of rotating frame magnetometry. So first, we initialize the spin state by irradiating green lasers. After that, we applied half-pi pulse to flip the spin state. Then we change the phase of magnetic microwave field, which corresponds to the change of the direction of magnetic field in the blockspheres. So then spin is locked in the same direction. So we can lock the spin state by irradiating this microwave field. So please consider the external field is applied to the electronic spins. If the frequency of external magnetic field is corresponding to the resonant frequency of electronic spins. If this frequency is the same, the electronic spin can rotate in this plane. On the other hand, this frequency is not equivalent to this frequency. The spin state cannot influenced by irradiating external field. So after that, we read out the spin state by irradiating microwave field and optical pulse. So the spin state, the final spin state is different. Different in the case of the external field frequency is same as resonant frequency of electric spins. So as a result, we can measure the external field by measuring the electric spin state of NV centers. So this is a preliminary result. You can see the peak at 4 megahertz. This is correspond to the external field measurement. So we can demonstrate for the first time by using the spin-locked technique in our sample. This is a very preliminary result. So the experimental condition is not optimized. So in order to estimate the performance of our magnetometry, we measure the T1 low in our sample. The T1 low is an important factor to determine the performance of this magnetometry. This T1 low is corresponding to the decay time of transverse component of Bloch vector during spin locking. So this is a result, and we obtained a very long T1 low, which is of the order of millisecond in our sample. So the expected performance of our sample is here. So we believe that we can detect the single proton spins using our sample and spin locking method. So here is a summary of my talk. So we demonstrate the doping control in nitrogen doped isotopically enriched CVD method. So as a result, we can demonstrate near surface doping by engineering the surface band structure. This surface band engineering can be done by changing nitrogen gas concentration and by changing surface termination. And we also demonstrate the lateral arrangement and doping density control by using the local off-angle engineered substrate. And also, I also showed the isotope engineering is so important to obtain the long coherence time. So finally, we demonstrate the quantum magnetometry using a spin locking system and our 5 nanometer thickness sample. Thank you very much for your attention.